So we'll get started. And today's a wonderful day. It's one of my favorite days. I look forward to every time I'm teaching calculus, because essentially today we're going to complete our list of functions that we know the derivatives of. We've been working our way up through it, and today's the day. And it's not just any function which is going to finish our list. It's the most wonderful function. Well, there'll be three that we talk about, but you'll know it when you see it. You're like, wow, that's just too good not to memorize. So we'll get there in a few minutes. But first, a problem. So suppose we have the following. F of x is said to be g inverse of h of x, and f prime of 2 equals 5. And then we have a bunch of information about g prime, and h at various values of x's, and we're asked to find h prime of 2. Now this particular question is from a recent final exam, which means this is the kind of question which we could reasonably ask you at an exam time, because we have. So let's think about it. How can we do this? Well, there's a couple of things we should observe. There's a prime here, f prime of 2, which says you should probably take a derivative of f. So you say, all right, well, let's take a derivative of f. So let's talk about that. So f prime of x. So that means we took the derivative of f, which means we have to take the derivative of g inverse of h of x. So we see there's an inverse here, which means we have to know how to take the derivative of the inverse. But the good thing is we just learned that. And so we know how to take the derivative of the inverse. And so the rule says if you're taking the derivative of an inverse function, it's 1 over the derivative of the original function. So right now, as we work through our derivative here, we work from the outside in. So we're working on the derivative of g inverse. So it's 1 over the derivative of g, so g prime of g inverse of h of x. Now, are we done? Probably not. Usually when I ask that question, the answer is no. What do we need to do? We need to do the chain rule. Now let's be careful here. What's the inside part? Is it h of x, or is it g inverse of h of x? It's the h of x. So you should really think about it as right now, this is the derivative of g inverse with h of x plugged in. And now we're going to multiply it by the derivative of h of x, which is h prime of x. All right, so that was actually the hardest part, is making sure we knew the formula for the derivative of the inverse, and we made sure we had correctly applied the chain rule. Well, now what do we do? Well, we know something about f prime of 2. So we should probably plug in x equals 2. So 5, that's equal to f prime of 2, which according to what we just did, that's 1 over g prime of g inverse of h of 2 times h prime of 2. Now we start working through our layers. All right, we don't know h prime of 2, but that's okay. If we did, we'd be done. So probably we should focus on this part here, this g prime of g inverse of h of 2. So do we know what h of 2 is? Yeah, we can find it. X equals 2, h of x, that's 4. Now, so that says we need g inverse of 4. Well, do we know what g inverse of 4 is? Well, we don't know g, but inverse, but we do know g. So we scan g of x until we see a 4. There's a 4. So what value of x gave us that? 6. So g inverse of 4 is 6. All right. Do we know g prime of 6? G prime of 6 is 2. So that becomes 1 over 2 h prime of 2. Now multiply both sides by 2, and we get that h prime of 2 is equal to 10. Full points on that problem. On to the next one. Good. I like this one. All right, any questions? Okay. Well, so what is today's topic? After we've had that mini endorsement. Well, today we're going to do the inverse trigonometric functions. All right. Now we're not going to do all 6, but we're going to do sort of 3 of them. And those 3 are usually enough to get what we want. So let's start by talking about just sine. Because oftentimes, once we see the sine, it can open up our eyes after we see the sine. So the sine function, if we look at it, it's what we call sinusoidal, which just basically means it goes up and down and up and down. Now, is the sine function, does it have an inverse? And why not? So, does the sine function have an inverse? No, it doesn't. What's wrong with the sine function? There's something called the horizontal line test. The horizontal line test says, if you draw a horizontal line, how many times can you hit the function? Once. If you hit it more than once, it can't be invertible. It turns out that for sine, you either hit it 0 times, because you might shoot for something outside of the range of sine, or you hit it infinitely many times, which is a bad number. 0 is okay, but infinity is not. So the way that this is solved is to say, okay, so when we talk about the inverse sine function, what we do is we say if we first restrict it to a particular part of the sine curve. So in particular, we take this part of the sine curve. That goes from negative pi halves over to positive pi halves. And if we restrict just to that part, we only have one time when we hit any vertical line. The other advantage of restricting to that interval from negative pi halves to pi halves is we hit every possible output that the sine function can get. So once we restrict, then we can take the inverse. And the inverse, we sometimes call it the arc sine. And that's the sort of preferred notation for me and a lot of people who like sanity. Other people like to write sine to the negative 1 of x. Now, the reason I think sine to the negative 1 of x is dangerous is a lot of people see sine to the negative 1 of x and they think to themselves, oh, don't you mean 1 over sine of x? And the answer is no. So don't confuse that sine to negative 1. When you see that negative 1, that means an inverse function when you see it attached to trig functions. For other functions, it oftentimes means 1 over. So be careful. Be careful. That's why arc sine is less ambiguous. So there's our sine curve. And if you were to go, you can actually see what happens. So the range is from negative pi halves to positive pi halves. Where's the domain? What numbers can you plug into arc sine? Negative 1 to positive 1. All right. So there's our sine. Now, tangent. Well, tangent looks something like this. So you have these asymptotes that happen. And so, for instance, you have an asymptote here at negative pi halves. You have an asymptote here at pi halves. Now, the nice thing about tangent is it is periodic, so it repeats. All trigonometric functions are periodic. For tangent, it turns out it repeats every pi. And so if you take, say, between negative pi halves to positive pi halves and shift it over, any multiple of pi in either direction, you'll get the same shape. Okay, all right. Now, same thing as before. Tangent by itself is not invertible, but once you restrict, then it is invertible. And so we restrict so that we only go between negative pi halves and pi halves. So essentially, we say, look, as far as the inverse goes, that's what we care about. And so to find the inverse, we would flip it. So remember that inverses you find by flipping across the line y equals x. So what happens? Well, you get this curve. Oh, what a beautiful curve. That is, I have to tell you, it's an emotional moment for me. This is arctangent. This is the most glorious function. Now, you may not be convinced of it now, but by the time you hit Calc 3, you're going to be like, wow, arctangent. You're going to become a believer. So there's a lot of wonderful properties here. Let's point some things out. So first off, notice these vertical asymptotes. What happened to them? They become horizontal asymptotes. So you get pi halves and negative pi halves. It also has some nice things. So for example, pass this through 0. For which values is arctangent defined? In other words, what can you plug into arctangent? You can plug in any number you want. So arctangent is defined for all numbers. It's a pretty nice curve. It's very smooth. We're going to see what that means. When we say smooth, it's differentiable. And it's bounded. These are wonderful, wonderful properties. It makes for many glorious examples. Many, many wonderful examples. All right. The last one we'll talk about is secant, which is 1 over cosine. And so secant, it turns out because it's 1 over cosine, where cosine is 0, for example, at pi halves and minus pi halves, you get asymptotes. It's never between negative 1 and 1, but it's between either 1 to infinity or negative 1 to infinity, depending upon whether you're the up part or the down part. So we usually restrict between there, between 0 and pi. If you take the inverse, you get the following function, which is the arcsecant function. And so the arcsecant function, this is not as nice as arctangent. It's not defined for all values, because if I'm in between negative 1 and 1, I'm not defined. It does have a horizontal asymptote, but not quite as nice. All right, so there we go. So those are the inverse tangent functions. So far, no calculus. Now we'll do some calculus. And our goal is to say, well, what's the derivative of the inverse trigonometric functions? So let's start with what I think is the best one, arctangent. So, here we go. We want to find the derivative of arctangent of x. So y is arctangent of x. We want to find dy dx. Now, we're faced with the dilemma. We don't know how to find the derivative of arctangent of x. So that's a big dilemma. But now we say, hold on, we do know how to find the inverse of arctangent. We know that derivative. What is the inverse of arctangent? Tangent. So we're going to take this relationship and use the fact that we know it's inverse. In particular, if y equals arctangent of x, then x equals tangent of y. Now what we can do is we can take the derivative of both sides with respect to x. And so as we do this, we're going to do implicit differentiation. Well, what's the derivative of the left-hand side with respect to x? The derivative of x with respect to x? It's 1. What's the derivative of tangent of y with respect to x? Secant squared y and dy dx by the chain rule. So now it's like, well, success! But not very satisfying yet. We'd really like to solve for dy dx, which we can, but the real thing that would be most satisfying is if we could put our answer back in terms of x, because we started with our original function was in terms of x, arctangent of x, and we want to end with something that has an expression involving x. So now we've got to put on our thinking caps. We say, well, secant squared y, if it was tangent squared y, that would be really cool. Now the reason I say tangent squared y would be cool is any time I see a tangent of y, I can replace that with x. So we start thinking, all right, trigonometry. We took trigonometry. We know there's a bunch of identities. Is there any identity that relates secant and tangent together? Tangent squared of y plus 1 equals secant squared of y. This is one of the Pythagorean identities. And so, in fact, it comes directly from the Pythagorean theorem. All right. Well, what does that allow us to do? Well, what that allows us to do is it says, you know that secant squared y, we can replace it by tangent squared y plus 1. And now, after you do that, you say, well, wait, tangent of y is x, so tangent squared of y becomes x squared. So you get x squared plus 1. And now you solve, And you get dy dx, divide through, is 1 over 1 plus x squared. Now that is beautiful. I mean, look at it. You have arctangent. That's an inverse trigonometric function. It's a trigonometry thing. On the other side, you get 1 over 1 plus x squared. That's not trigonometry at all. That's really algebra. So it's very unexpected. It's like, wow, that's amazing. It makes you want to circle it several times and maybe put like a star by it. So that's a cool fact. So this is the last one that I expect you to know from now until the end of Calc 3. The derivative of arctangent is 1 over 1 plus x squared. Good. Now we may want to try to convince ourselves that at least it's reasonable. Let's think about some things that should be true. Let's go back to our picture of arctangent. So let's think about, see if we can get, there we go. So here's our derivative, here's arctangent. What happens to our derivative of arctangent as x goes to infinity? What's happening to it? Now the whole expression gets very small because you get a large number in your denominator, which means that your tangent line should have very shallow slope. In other words, as we get large, our tangent line should look flat. And that's what's happening, because when I'm approaching that asymptote, I am approaching a flat tangent line. Where should I expect the derivative to be largest? Which value of x will this be big? Well, if I want the whole expression to be big, you should make x squared as small as you can. And how small can it be? 0. So it should be most steep at 0, which that's what it matches. And in fact, what we should expect, it should be shallow, should increase as we get to 0, then after 0 it should start to shallow out again. So that this is matching the behavior that we see, which is good because that is the right derivative. We know that. All right, well now that we've got the rule, let's practice. So let's find a couple of derivatives. Now the first one doesn't have anything to do with arctangent, but it's good to sort of compare. What's the derivative of natural log of 1 plus x squared? What does that give us? So when you have natural log, it's 1 over the inside. Anything else? Times the derivative of the inside, which is 2x. So oftentimes it's not too surprising to see a log of 1 plus x squared mixed in with an arctangent, because they actually end up, when you take derivatives, they'll have the same denominator, so it makes it a little bit easier to work with. But there is a difference. When you take the derivative of arctangent, the numerator is 1, whereas when you have this log of 1 plus x squared, by the chain rule you have that extra 2x term showing up. What's the derivative of arctangent of sine of x? What rule do we need? It's the chain rule. The sine is a function inside of the arctangent. So, according to the rule says it's 1 over 1 plus the inside squared. See, it's arctangent of x is the inside, 1 over 1 plus the inside squared. So, 1 over 1 plus the inside is sine. So I'll write this as sine of x squared, or you could write sine squared of x. And then what else do we need? Times the root of the inside, which is cosine of x. All right? The derivative of arctangent of x squared. What will that be? 1 over 1 plus x to the 4th power, which comes from x squared squared, and then 2 times 2x. And of course, you can write that as 2x over 1 plus x to the 4th. All right, whoops, sorry. How about the arctangent of square root of x? What would that be? 1 over 1 plus square root of x squared, which will become x. Anything else? And if it helps, square root of x. What's another way to write square root of x? X to the 1/2. So 1/2 x to the negative 1/2. Now, if you clean this up, well, 1 plus square root of x squared becomes 1 plus x. Then there's a 2 from this half. And this negative means that you move it downstairs, so it becomes 2 root x. All right. And how about the derivative of arctangent of e to the x? What would that be? One over 1 plus, hopefully you're seeing there's a pattern, 1 over 1 plus e to the x squared, and then times the derivative of e to the x. So you notice, this 1 over 1 plus e to the x squared also is the same as 1 plus e to the 2x. But we're not taking the derivative of e to the 2x, it's the derivative of e to the x. So remember what's on the inside. It was like the problem we started off with. Pay attention. What's the inside part? Because that's going to be important. All right, well, let's try a few more problems. Find the tangent lines to y equals arctangent of x at x equals 0 and at x equals 1. So if we want tangent lines, what things do we need? Points and slopes. And so we're going to need a derivative. So the good news is we kind of know a little bit about the derivative of arctangent. What is it? 1 over 1 plus x squared. Good. So let's go through our 2 points. So at x equals 0, well, our point is going to be 0, comma. How do we get the y-coordinate? Plug it into which part? Arctangent x or 1 over 1 plus x squared? The arctangent. Okay, what is arctangent of 0? Arctangent of 0 is 0. Yeah, so that's good. That's not so bad. Well, what's our slope? Well, plug 0 into your derivative, and what do you get? 1. So y minus your y value, which is 0, is equal to 1 times x minus your x value, which is also 0, or you end up with y equals x. Okay, well that's pretty nice. What a nice line that tangent function has. Excuse me, that arctangent function has. Okay, well that's at x equals 0. Let's do another point. X equals 1. So our x value is 1. And now the question is, what's arctangent of 1? Now if you're not sure what arctangent of 1 is, you can change the question. And instead of saying arctangent of 1 equals something, the question is, tangent of what gives 1? Do we know an angle where the tangent produces 1 as an answer? Pi fourths, or 45 degrees. So the arctangent of 1 is pi fourths. So this is another thing that makes arctangent nice. You can actually evaluate it at 1, you get a reasonable answer. What's the slope at 1? Well, plug 1 into the derivative. What do we get? 1/2. We get 1/2, because we get 1 over 1 plus 1 squared. So you get a half. So we have a point and a slope. So y minus your y value, which is pi fourths, is equal to 1/2, which is your slope, x minus your x value, which is 1. And that's it. All right, let's do another example. For time t, which is greater than or equal to 0, the position of a particle is given by s of t is arctangent of t squared. Determine when the acceleration of this particle is 0. All right, so for after acceleration, how do we go from position to acceleration? Second derivative. Because position, if you take one derivative, you get velocity. If we take a derivative of velocity, we get acceleration. That means we're 2 steps away. So let's start by taking our first derivative. What is s prime of t? So the derivative of arctangent t squared would be 1 over 1 plus t squared squared times 2t. Or if you like, 2t over 1 plus t to the 4th. So there's our s prime. All right, and now we've gone from something with arctangent to something which is actually more reasonable to work with. Well, maybe not more reasonable, but at least algebraic. How would you take the second derivative? What rule do we need? Quotient rule. Or if you don't like quotient rule, you can always do every quotient rule as a product rule and a chain rule by noting that 2t over 1 plus t to the 4th is 2t plus, 2t times 1 plus t to the 4th to the negative 1. So if you don't like the quotient rule, just say, aha, do it that way. But apparently people really like the quotient rule. So the quotient rule says take the bottom, 1 plus t to the 4th times the root of the top, which is 2, minus the top, which is 2t times the root of the bottom, which is 4t cubed. And then we're going to take that and divide it by the bottom term squared. Now, before we simplify, let's just think about where we're going. What is it we're after? Well, we want when the acceleration is 0. So we found acceleration. We haven't simplified it yet, but we want it when it is 0. So that doesn't mean we plug 0 in. What do? We set it equal to 0. Now, when you're setting something equal to 0, that's a fraction. What that really says is I need the top to be equal to 0. Notice the bottom will never be 0 because it's always going to be at least 1. So that says let's set our numerator. So let's see. Well, let's write this out. So we're going to get 2 plus 2t to the 4th if we distribute the 2 through. 2t times 4t cubed, that would be 8t to the 4th. And that should equal 0. Our 2 minus 6t to the 4th should equal 0. So we can move the 6t to the 4th across. 6t to the 4th equals 2. So what does t to the 4th equal? A third. So what does t become? All right, the 4th root of 1/3. Now, is that our answer? Yeah, you're so used to me asking the question and be like, no, but it is our answer. Because what were we looking for? We were looking for a when. So if we're looking for a when, that's our input. For what input do we get an acceleration of 0? And the answer is when we choose t equal to the 4th root of a third. Okay, good. All right, well, that's arctangent. We should, of course, do the same thing that we did for arctangent for arcsine and arcsecant. So we'll start with arcsine. So you're going to see it's the same process. So you start with arcsine. Y equals arcsine of x. X equals sine of y. That's because they're inverse functions of each other, so we can rearrange. Take the derivative of both sides. Do you remember what the derivative of sine is? Cosine. So we're like, okay, so we get 1 equals cosine of y. Now, if you think back to arctangent, we said, well, we had that secant, and I want to replace secant by tangent. Is there something that we can do that I can make cosine become something in terms of sine? Well, what do we have? Cosine squared plus sine squared equals 1. So cosine of y is the square root of 1 minus sine squared of y. So that's kind of true. Now, you should be very skeptical and say, there's a problem here, Steve. Is there a problem? Would you like to talk about the problem? What's the problem? Do you see the problem? Shouldn't there be like a plus minus here? Right? Isn't that a problem? Because when we take square roots, there's like two possibilities. Now, what's my get out of jail free card? Remember, we're dealing with arc sine of x. What did we say about arc sine of x? Do you remember what we said? Where does arc sine of x fall between? Negative pi over 2 and pi over 2. Now, look at your cosine function. If you graph cosine function, and we'll do a quick graph here, between negative pi over 2 and positive pi over 2, what's true about the cosine? It's greater than or equal to 0. So in fact, this is correct to say that cosine of y is the square root of 1 minus sine squared. So we haven't actually cheated. It just looks like we cheated, but we were actually okay. So now the rest of it's pretty straightforward. We replace cosine by the square root of 1 minus sine squared. And that becomes the square root of 1 minus x squared. And therefore, the derivative of arc sine of x is the square root, is 1 over the square root of 1 minus x squared. All right. Now, I'm not going to put extra layers on this one. It's kind of not the most obvious one to remember. I personally don't memorize it. I just know how to rederive it. I kind of know it now because I spend a lot of time teaching the class. And usually what happens is after about the third or fourth time you teach calculus, you start remembering these things. So if you're ever having a hard time, like, man, I'm having a hard time remembering all these formulas, just teach it a couple semesters and boom, you'll know it. You'll know it. So I can't promise you that you won't see it, but I will say that 95% of the time, we don't ask for this on a test. But there's always that 5%. Okay. For the 5%, just rederive it. It's really quick. For arc secant, it's going to be really quick. Same process. X equals secant, derivative of secant. Do you remember that? Derivative of secant is secant tangent. Now, the good news is, this secant is going to be really easy to work with. It goes straight in. What do we do with the tangent? Well, we use our identity. So tangent squared y plus 1 equals secant squared y. So tangent of y is equal to the square root of secant squared y plus 1. And then I'm going to put a little asterisk here. This truly did cheat. And I'll clarify what the cheat is in a second. So you replace tangent with that expression, and you get x over the square root of x squared minus 1. And therefore, the derivative of arc secant of x is 1 over x square root of x squared minus 1. And here's the asterisk, which says I need x to be greater than 1. Now, what happens if you're like, I really, really want it to be true for all x? What's the right formula for all x? Well, if you want the formula that's true for all x, you add in an absolute value. That makes it true for all x. But there's a little bit more work you have to do. You have to do 2 cases. But other than that, it's the same process. So, and that's the arc sine and arc secant. All right. Well, let's do another problem. Find the derivative of tangent of arc secant of x. So when we need arc secant, we'll come back and put it in. All right, so if I'm looking for the derivative of the tangent of the arc secant, what rule do we need? We need the chain rule. All right, so we start by saying, well, the derivative of tangent, secant squared. So that's secant of, well, we plug into secant, which is arc secant, and then square. So this is my secant squared. I'm just writing that in a way that's going to be very convenient in just a moment. But that's secant squared. And then what? And then the derivative of arc secant. And so we have the derivative of arc secant. We just found that. So we're going to assume we don't need the absolute value. So that's going to be 1 over x square root of x squared minus 1. Okay, let's see if we can simplify anything. Well, there's not a lot you can do with this expression. What about secant of arcsecant? Is there anything you can do with that? What does it become? It becomes x, because these are inverse functions of each other. So arcsecant takes x and produces some number. Secant takes that number and says, whoa, whoa, no, go back to where you came from. And so whatever you do, after you compose those two together, you get what you started with. So what we have is x squared times 1 over x squared of x squared minus 1. Of course, you can write that as x over square root of x squared minus 1. And now you're thinking, there's a lot of white space here. Okay. Well, let's do it a different way then. All right. It's always fun to do things a different way. So let's try a different method. So the derivative of tangent of arcsecant of x. And for our second method, let's, before we take this derivative, ask if we can rewrite what is tangent of arcsecant of x. So let's start by looking at the inside. Arcsecant of x, what kind of thing comes out of an arcsecant? So let's think about secant. What do you normally plug into secant? What type of thing do you plug in? Well, it's a trig, which means what are we plugging in? What type of thing do we plug in to secant? What type of thing do we plug into secant? A is a really good choice. R is not a good choice. I think that someone's trying to sabotage you. N, okay, someone? Angle. Yes, okay, all right. Good. You mastered your trigonometry. You plug angles into trig functions. So we plug angles into secant. So now the question is, what's coming out of arcsecant? Angles. Because what you plug into secant is what's coming out of the inverse function for secant. So this is an angle. Well, let's give it an angle-like name, theta. So theta is arcsecant of x. Well, another way to write that is secant of theta is x. Or x over 1. You're probably thinking that's a strange way to write x. But if you think about where secant comes from, it comes from ratios in a triangle. So, in terms of the sides of a triangle, what is secant? Hypotenuse over adjacent. So secant is related to cosine. Secant is 1 over the cosine. So if cosine is adjacent over hypotenuse, flip it. Secant is hypotenuse over adjacent. The length of our missing side, well, you do a Pythagorean theorem, it turns out it's square root of x squared minus 1. So, what is tangent of theta? Well, it's the opposite over the adjacent. So it turns out that we could have rewritten tangent of arcsecant as simply square root of x squared minus 1. Or if you like, that's the derivative of x squared minus 1 to the 1/2 power. Let's take this derivative. So what happens? Half comes down. X squared minus 1 to what power? Negative 1/2. And then, derivative of the inside is 2x. The half and the 2 cancel. We're left with an x upstairs. This negative means it's downstairs is the square root of x squared minus 1. And you'll see these match. You could actually use this to figure out what the derivative of arcsecant is, because you could have said, well, if I didn't know the derivative of arcsecant, I could just put a placeholder here for the derivative of arcsecant and then compare the two and see what it had to be for it to work out. Well, we have enough time for one more quick problem, I hope. We'll see. Find the tangent line at the following point, 1/2, comma, 1/2 square root of 3. To the implicitly defined curve, 3 arctangent y over x is pi plus 3 natural log of x squared plus y squared. So it turns out that this point, 1/2, comma, 1/2 root 3, satisfies this relationship. Now you're probably thinking, I'm a little bit skeptical, Steve. I'm not sure it actually does. Yes, it does. But if you need a little bit more convincing, you would see that this is 3 arctangent. Y over x becomes square root of 3. Well, do you know what the arctangent of square root of 3 is? It's a 60-degree angle, also known as pi over 3. 3 times pi over 3 gives us pi. If you take x squared, you get a fourth. Y squared gives you 3/4. A fourth plus 3/4 is 1. And log of 1? Log of 1 is 0. So you get pi equals pi plus 0. So it is actually a point on the curve. It is an implicit relationship because we don't want to solve for y in terms of x, because that looks hard. Also because we can't solve for y in terms of x, because it is very hard. All right. So what do? Well, we follow the rules. So we're going to take the derivative of both sides with respect to x. So let's start with the derivative of, actually, before we take the derivative of both sides, let's divide everything by 3, because I suspect that will disappear. So arctangent y over x is pi thirds plus natural log of x squared plus y squared. All right. So I'll write that down over here just for convenient reference. So arctangent y over x is pi over 3 plus natural log of x squared plus y squared. All right, let's start by taking the derivative of arctangent of y over x. So, start with the derivative of arctangent. The derivative of arctangent is 1 over 1 plus the inside term squared. Okay? That's always our rule for arctangent. 1 over 1 plus the inside term squared. Now, multiply that by the derivative of y over x. What rule do you need to take the derivative of y over x? The chain rule. Okay. Well, sorry, we're taking the chain rule, and then we're going to take the product rule. Sorry, the quotient rule. Eventually, we're going to run out of rules. We'll get the right one. All right. So there's a chain rule because we're applying the chain rule, and then we're doing a quotient rule. Okay, so you take the bottom times the derivative of the top minus the top times the derivative of the bottom. Well, the derivative of the bottom is 1. And when we take the derivative of y, we put y prime. And divide by the bottom term squared, x squared. Okay, are we done with the derivative of the left-hand side? Yes. Yes, we've worked it through. Now we move to the right-hand side. Okay, the derivative of pi over 3. It's 0 because it's a constant. Well, we got a break. Okay, 0, so now we're doing this part, plus derivative of natural log, 1 over the inside. You leave the inside completely alone, and then multiply by the derivative of the inside, 2x and 2y prime. Very good. Are we done with the derivative of the right-hand side now? Yes. Okay. Cool. Now, before we evaluate, I will point out one thing. If you multiply here, notice you have an x squared, and here you have a y squared over x squared. So you get x y prime minus y over x squared plus y squared. And that's going to equal 2x plus 2y y prime over x squared plus y squared. So I'm multiplying the x squared through. So the x squared cancels on the last term. That's why you get the y squared, and then x squared times 1 is x squared. What happens next? Well, we could say, look, we're not at x, y equals 0, 0, so we're not dividing by 0. And since that's on both sides, I could actually multiply through and cancel it off. So the x squared plus y squareds go away. All right, so we don't have to worry about them. And then it's time for us to start plugging in. So x, wherever I put an x, I put a 1/2. Where I see a y prime, what do I put? I put y prime because I don't know what it is. Where I see a y, I put a square root of 3 over 2 equals 2x, 1, plus 2y, square root of 3, and then times y prime, because I don't know what y prime is. I'll go ahead and multiply through by 2 on both sides, just so I get rid of all my fractions. So 2 plus 2 root 3 y prime. And now you do a little bit of rearranging, put all the y primes together, put all the things that aren't y primes together. So 2 square root of 3 minus 1 times y prime, so I put all the y primes together, is equal to minus, and they're both going to be negative, so I pull up minus out, of 2 plus square root of 3. So the derivative is negative 2 plus square root of 3 divided by 2 square root of 3 minus 1. Now, what do we do with that? Well, that's our slope. Do we need to simplify? No. No. Okay, so that's our slope. Do we have our point? We were given our point. So y minus our y value, square root of 3 over 2, is equal to our slope, negative 2 plus square root of 3, divided by 2 square root of 3 minus 1, times x minus our x value. And there was our tangent line to our implicitly defined curve. Okay, good. Well, that's it. We're done for today. All right, see you next time.